All right. Okay, shall we get started? Thank you all for coming to see my talk. It's called Implementing a JVM in Java and Rust. My name's Ben Evans, for folks that don't know me, and I use he, him pronouns. So for just a quick rundown on some of the things that I've done over my occasionally unusual career, I'm currently principal engineer at New Relic, based here in Barcelona. Yay. So check out my Barcelona t-shirt, which has got all of the landmarks from various places in BCN. Before that, I helped found JClarity, and I spent about 15, 20 years in London working for startups and financial organizations of various kinds. I've also done a bunch of stuff in the community, so I'm a Java champion and a rockstar speaker. I spent 6 years serving on the Java Community Process Executive Committee, which sounds really impressive and was actually a lot of meetings and not enough technical work. But, you know, someone's got to help write the standards, so there we are. And, of course, the London Java community, where I've been involved for, I guess, for about 10 years now. I don't really, you know, given that I live in Barcelona now, I don't really do that much anymore, except, of course, for Adopt OpenJDK. Right, so let's turn to our goals for the talk today. So the goals of the implementation are really about exploration and teachability and fun. You know, I am not setting out to replace Hotspot here in any way. Hell, I'm not even setting out to replace Avian. Hands up if you know what Avian is. Nobody. Okay, wow. So Avian is another open source implementation of the JVM. It's actually written in C rather than C++, and it's probably one of the more understandable ones that there are out there. If you've ever tried to read the Hotspot source code, who's tried to read the Hotspot source code? Yes, I see Andre in the audience, so I was hoping at least one person put their hand up. There we go. And how was it? Who likes reading the Hotspot source code? Yeah, that's about the number I thought I'd get. Nobody. It's written in this kind of impressively 90s dialect of C++. So even for C++ programmers, it just looks kind of weird reading Hotspot source code. And it's certainly not the place where if you're just interested in the JVM and understanding how it works or how you could implement it, Hotspot is a really bad place to start. So this point about teachability here, this is really what I'm aiming for. I'm aiming to produce just a simple, fun thing which will let you see how you might start to implement a JVM. Well, what language would I choose to write it in? Well, Java, because that's one of my primary languages that I write all the time. We know why we like Java. It's easy to structure a Java program well. It's a good teaching language. If you write clearly in Java, it can be understood by basically any Java programmer. You know, as Brian was telling us this morning, you can write bad code in any language, and Java is no exception. But well-written Java really is a joy to behold, or at least I think so. So I might want to implement in Java. And in fact, when I said implementing a JVM in Java and Rust, the surprise, the twist in the tail that I can now tell you, is that it's not one implementation that's written in Java with bits in Rust. It's actually two implementations. Or as we'll see, it's really the same implementation twice, once in Java and once in Rust. And the Java implementation is actually the one that I wrote first. So it's kind of my prototype of how to write a JVM. So when I came to think about learning a new language, as I periodically do, I wanted a language which I didn't know, and a language which had something new to teach me. Because as I've said in a couple of conversations with people, I think some of them even in this room, every time that you learn a language, it must be genuinely different from the languages that you already know. Now, if I went and got a job as a C# programmer, I can't imagine doing that, but I could, a lot of what I already know about Java would translate over into C#. And in fact, when I have consulted on .NET projects, that is actually the case. Even down to being able to see similarities in the design decisions of the virtual VM. There is a lot of similarity between the languages. So I wouldn't necessarily feel that personally and intellectually I would get a great deal from learning a language like C#. You know, Python, sure. Lisp, Haskell, why not? But not something which is similar to languages that we already know. So why Rust? Well, I've been curious about it for a long time. I've never written any, you know, beyond downloading it a couple of times and writing Hello World. But that never really teaches you anything. Hello World, I think we as programmers, we get a little too hung up on it. It's a good example of the anti-pattern that I sometimes like to call easy things are easy. So I wanted a real project, something to really test myself out on in Rust and see if there was something new about programming that it could teach me. And did it? Well, let's find out. So here's what a JVM looks like. Well, if we're going to build one, three of the kind of main subsystems of the JVM are represented here. What's missing, of course, is garbage collection, right? So that's really a runtime data structure. When we think about implementing a VM, that's what our heap is going to be. It's just going to be another data structure in the implementing language that we write our VM in. Okay? The other parts, though, we're going to have a class loader, sure. We're going to have an interpreter. Am I genuinely going to build a JIT compiler? Well, no, I'm not, because that's going to take us too long and too far afield, and actually those things are hard. I might leave that to the clever folks who are producing Graal, and let's not even talk about C2, eh? So yeah, so the parts we're going to build fundamentally are the interpreter and the class loader. So let's just do a few basic bits about how interpreters and bytecodes work, and then we'll also need to talk about the areas of memory, the parts of the runtime system of the JVM that we're going to need to implement. Okay, so remember, the interpreter is the code execution environment. It is stack-based. There are no registers in the JVM. Okay, the JVM bytecode does not have an accumulator or any other register. So when I say that it's stack-based, I don't just mean in terms of the stack frames that we're used to as Java programmers, or what I might call a call stack. Of course, all structured programs, since we invented the idea of the subroutine back in the 1960s, are stack-based in that sense. When I say the JVM is stack-based, though, I mean something different. I mean that because it lacks registers, it needs a temporary evaluation area. So it has an evaluation stack as well as its call stack. And as we'll see, that's a critical difference between JVM and machine code. Okay? So what is bytecode? Hands up, who did a compiler course when they studied CS at university? A few people. Okay. So if I say an intermediate representation, an IR, you'll know what I'm talking about. And actually, bytecode really is one of those. If you talk about a compiler having two halves, the front half and the back half, where the back half is actually the part which generates the actual machine code, we can see that Javac isn't really a compiler. It's really just the front half of a compiler. It takes human-readable source code and it translates it into an intermediate representation. You might also think about an abstract syntax tree. Hands up if you've worked with abstract syntax trees. A few people. Okay. Yeah, and again, bytecode is not exactly an abstract syntax tree, but it's not very far away. And so all those lovely libraries like cglib and asm and all of those things which transform bytecode are usually operating on something which is close to an AST representation. So loosely, and if we're kind of relaxed about this, and hey, nobody here is a compiler theorist, we can say that bytecode is kind of halfway between human-readable source and machine code. It's produced from source code, and some of the high-level features that you expect in the Java language are compiled away. It is actually not possible to exactly reconstruct a Java language program correctly or precisely in all cases from the bytecode. Information is lost when you transform from source code to bytecode. Not a lot, and it's a surprisingly few amount of corner cases, but stuff is got rid of when you compile away. For example, the loop keywords, for and while, they're gone. No such thing as a for or a while in Java bytecode. Instead, we have if opcodes and goto opcodes, just branching and loops. That's all that we have, and everything will be boiled down to that. There's also good to remember, and this is another reason why bytecode is not at all really that similar to machine code. Opcodes in JVM bytecode are a mixture of what you might think of as high-level or complex operations and low-level operations. If I do integer arithmetic, and spoiler, we're going to do quite a bit of integer arithmetic in a minute, that's a very low-level operation. It directly translates into machine opcodes very, very easily. Method invocation, on the other hand, is not. Method invocation requires some fairly sophisticated support from the runtime, and it's actually one of the more complicated things that we can do. But yet it's still represented as a single instruction in the bytecode. Invoke virtual, invoke special. If you're feeling particularly sophisticated, you might even consider an invoke dynamic. But all of them are simply a single instruction, so that we consider them a high-level instruction compared to the arithmetic ones. So okay, what else are we going to say about the interpreter? Well, we'll deal with the integer arithmetic first, but we also, sooner or later, have to deal with classes. The JVM is a fundamentally object-orientated system. Just checking, is Brian here? Am I going to get shouted at for that? No, it very much is. Yeah? You cannot run on the JVM unless you have a class file. The JVM interprets classes, execution starts with classes. There is no other representation of a program that's possible. For C++ programmers, we might say there are no such things as free functions. Everything must live inside a class at some point. So as you might guess, we're going to have to deal with that. We're going to actually have to understand the class file format, and we're going to have to deal with classes as we find them. So how are we actually going to implement our JVM? Well, the simplest implementation of all is a method. Haven't said what language here. You might guess that it's Java. You might be right. But it's just a method, and what it's going to do is it's going to execute a byte array. Methods start life as just arrays of bytes. That's what bytecode is. Yeah? So we're just going to call this method in our interpreter called exec method, and we're going to pass it the bytecodes corresponding to the method that we want to interpret. And what the structure of that method, exec method, will look like is a switch statement inside a while loop. So we're going to take one bytecode from the stream, look at the byte, and in a switch statement, we're going to decide what to do with it based on what its operation code, its opcode, actually is. Okay? Then we perform that in a case statement. And then we fall out of the switch statement, and we check to see if we've ended the method. And if we haven't, go back to the top of the while loop, take another bytecode, switch on it, and so on and so on and so on. So we'll end up with a method, a main loop, which looks something like this. Each of these methods is going to start by you pass in a bunch of bytes. You create a new evaluation stack. Yeah, I did tell you that there was going to be a stack where we calculate temporary values from. And then we have this while loop. And I know that my style is a little strange, but I definitely always like to label my while loops. Some people tell me that this is terrible and unnatural and all sorts of things, but never mind. So while we're in the loop, we take an instruction from the byte array, and of course increment the current location where we are, switch on it, and then we'll have these symbolic constants for each of our cases. Okay, sound good? Everyone following so far, I hope? Good, good, good. By the way, Hotspot doesn't actually do that. If you actually look at the source code for Hotspot, even in C++, there is nothing like this, because it doesn't build one. It actually uses what's called a template interpreter, which basically involves building a dynamic dispatch essentially every time the machine starts. It uses a lot of assembly language code, which basically means that Hotspot's interpreter is very, very fast. But the expense of that is it also increases the porting overhead. If you want to take Hotspot and move it to a new platform, there's quite a lot of work that's involved in that. It's also the case that the interpreter also has to call back to the VM for a lot of complex operations in Hotspot. For example, looking up the constant pool. Okay? But don't worry about any of that. For our purposes, we're going to do it the easy way. Okay, let's talk about the areas of memory that we need. We need per method local variables. We need per method temporary evaluation stack. Remember, no registers. And we'll have an area for each class of what we call a constant pool. This is a useful area of stuff that the method needs in order to execute. Okay, I'll say more about it in a sec. And then, of course, finally, we have the global shared heap, which is shared between all methods and all frames in the call stack and between all threads. It looks a bit like this. So for each of the functions, the methods we've called on the stack, we have some local variables here, or possibly entries in the evaluation stack local to each method. And those things, of course, are pointers. So here's another interesting thing. In order for this to make sense, we need to know what elements in our local variables and on our stack. Are they primitives or are they pointers? Because if they're object references, pointers to us, we have to follow them into the heap. So Java, at a low level, always knows what the type of a value is. It's said to be an exact form of storage. Is it an int? Is it a pointer? Okay, so let's meet our implementation. It's called Ocelot, and it's this little cat face here. So what should we do first of all? Well, I'm a big believer, you see, in TDD. I'm a believer in just doing things, the simplest we can possibly do first. And what could be simpler than just some integer arithmetic? Well, we're also going to need a return opcode as well, so that the method actually comes back to us. But it seems to me that if we start with just those, we could actually build an initial interpreter. Okay, it's not going to interpret everything, and it can't handle class files, but it's a start, right? So, always check which branch you're on. Is that font size big enough at the back? Yes? Cool, excellent. So here are opcodes, and I've done something slightly different here. You remember in the first slide I showed you, it was actually just a byte, and it was an array of bytes. Well, for reasons of program clarity, I've actually decided to make this an enum, so these are actually type safe. Okay? So here are all of our enums, and you can see that each of them has an opcode associated with them. So these are the hex values which correspond to each operation. And I haven't told you a lot about what each one does, but you can see that what we have here are things like I_add. It's pretty obvious what that's going to do. There are two integers on the stack, and it's going to add them together and replace them with the result of adding them together. Okay? We have iconst. Guess what that's going to do? It's going to load a constant onto the stack. And you can see that there are predefined constant loads for -1 and 0 through 5. Okay, so far so good. We also have the by push opcode. That one is useful because what it does, and you'll notice that it actually has a second argument. This is the number of parameters that this opcode takes. So if you have a by push opcode in the stream, then the next thing that will come out after it is a single byte value representing a byte to be pushed onto the stack. Okay? So with these kind of basic operations, we can actually build, I would say, a few test cases. And sure enough, down here is iReturn, which basically says this method returns, exit out of the switch statement interpreter, and return this result back to caller. Okay? Now, caller for us, of course, is going to be, oh, that's nasty. So, I really hate the fact that in IntelliJ, it doesn't seem to want to. That's better. So I just need to close all these and reopen them. Never mind. So here we go. Here we have our interpreter, our test class. We've got a thing called interpreter main, which we haven't met yet. That's actually the main loop with a similar structure to the one that we saw before. Okay? So let's try this one, some integer arithmetic. Okay? So iconst1, and I'm using another trick here, which is that because these things are enums, I can call a method on them. And the method capital B, have a guess what that does. Returns the original byte representation for it. So I actually can get back a byte buffer, but I can use nice symbolic constants for all of these in there. So I can actually write, bytecode using the names of the byte codes here. So I'm going to iconst1, I'm going to iconst1, I_add, and I_return. So I'm going to put the constant 1 on the stack. I'm going to put the constant 1 on the stack. I've got a stack with 2 ints in it. I'm going to I_add on them, and I'm going to get 1 integer left on the stack, which I'm then going to return. Okay? Makes sense, right? Cool. So now I can just write a perfectly standard, nothing out of the ordinary JUnit test. It's JUnit 4. And I'm just going to assert that return value from executing this is 2. I'm also going to check the type of this as well, because remember I said values in the JVM have to be typed. So I've got a simple enum which indicates the possible types, and I'm asserting that this is an int as well. Okay? Great. So I'm going to do a few more of these, and now I'm just doing TDD, right? And I can just do this, and hopefully I've sacrificed the right things to the demo gods. This is actually going to pass its test cases. And it does. Hooray. That was a close one. Okay. So let's actually step into the interpreter main now. And sure enough, there's my table of opcodes that I've built, and I do a little bit of shenanigans just so that when I'm adding new opcodes to the system, if I ever mismatch between what opcodes I put into the opcode enum and which opcodes are actually present in the interpreter, that I get a sanity check failure. So that's just a bookkeeping exercise for me while implementing it. Here is the actual method. Well, it's got a few more parameters than I told you about, such as the class name and stuff, but I don't really mind about that. You will also notice, of course, that there is a I've just basically dummied up the other values. You see, I've passed in buff, and the other ones are all dummied. It's really the bytecodes we care about. Sure enough, there is my evaluation stack that we talked about, which in this code is called into eval stack. We take the byte from the stream, we look it up in our opcode table, so we have the correct opcode corresponding to the byte. We do a quick sanity check on that to make sure that if we can't look it up, if we've encountered an opcode that we don't recognize, that it will fail immediately. So again, this is an incremental thing about building the VM up slowly over time. We then fall into the switch statement. There's some nasty pre-declaration of a whole bunch of stuff up here. That's necessary because of the syntax issues associated with the switch statement. So that's one of the nasty legacies of the C-like switch statement that Java has that Brian was referring to. Essentially, each case arm is not considered a separate lexical scope. So you actually have to declare your variables in a higher scope, which is just annoying. So here are our operations. What are we going to do? Let's look at iconst, for example. Iconst is going to load the constant 1 onto eval. Now, what was eval? It was our interpreter stack. So sure enough, here, this class is an extension of a stack of JVM values. And a JVM value, just show you that, is just, well, we don't have records yet, so I've had to model it as a class. It's a tuple. It has a type and a value, and that's it. But notice, and this is something I'll come back to later on, how the value is actually being represented. It's being represented as a long. This is the nearest thing we have in Java to a general bit container. What I actually want here is just some bits, but I can't get that. So the way that I actually model it is with a primitive long. Don't worry if that doesn't make sense yet, it will soon. And here are the instructions that we've built on top of our stack. And here we are, there's iadd. You pop the two values off, you add them together, and you push back an entry that you've made of the two newest ones. Okay? So all of the low-level instructions on our stack are actually implemented here. What else? There's, so pops and nops are pretty straightforward. iReturn, of course, just returns from this method back to caller the evaluation. So when we run our test case, when we hit the iReturn, we just return top of stacked into caller. Okay? So far, I hope you people are thinking, oh, this is okay. I could probably write this. Yeah? That's good. That's the aim. This is not supposed to be complex or difficult code, but this is supposed to show you the structure of the interpreter. Okay. So let's come back to the slides. Any questions so far, by the way? No? Good, because we're going to start speeding up. So this is what we built. We built some initial opcodes. We built an interpreter main loop. We understand what a JVM value really is. It's something to indicate what the type is, and it's a collection of bits. We've built an evaluation stack. I didn't show you the local variable table, but it's there as well. And we built some test cases. So what should we try to support next? Load and store to local vars, so some store and load operations, so that we can actually, instead of just using constants or things that we can use using a by push operation, what about actually having a local variable and storing stuff in it locally in the method? Yeah, that sounds good. At this point, we can also add branching and jumps, so if operations and gotos. Okay, what else could we do? Well, at this point, we could add more primitive types. We could. But actually, we don't want to do that, because it turns out that by adding more primitive types, all that happens is the interpreter main loop just gets bigger and bigger and harder to understand. We've seen how the ints work. Please just take it on trust that if you add double and long and various other things, the same thing will also occur. Okay? Great. So let's go back to the IDE. Back to the command line. That's what I meant. Because rather than having the full code available right at the start, I actually just have some branches so that I can take you directly to a slightly more complex version. Okay, so now you see we've got things like if, and goto is somewhere in here. Where's goto gone? There you go. So goto takes 2 bytes after it in the stream. And if we look at the goto opcode, sure enough, there are the 2 bytes in the stream that it takes after it. And from those, you compute where to jump to as a relative offset. Okay? So if we now look at the test jump branch, there are some more test cases here. So what we're going to do here is we're going to load 2 constants onto the stack, add them, and then go to the value following, which is 1 byte on. Now notice we have 0xFF here, which is an undefined opcode. So if we saw that, and the interpreter ever saw that byte, it would immediately error out. But it doesn't, which indicates that we must have jumped over it and reached the I return. Okay? So this byte here is, I think the actual value for it is impdep for implementation defined, but it doesn't, it's an illegal bytecode in any case. So let's just run this and see what happens. And you can see that I have this kind of BDD style for my test case names. So jump over unimplemented opcode. Yeah, and it works. So sure enough, we're doing the jumps. That's good. We've got an if test here where we do some other things. And look, we've got store and load implemented as well. And yeah, that works too. It's great. So let's come back to the interpreter main. Is there anything else you want to say here? I think that's it. The load and store stuff is actually now working on this thing LVT, which are the local variables. So effectively, it's a thin wrapper over an array of JVM values. There's a few methods defined upon it, but essentially in Java, we like to model things by giving it a proper name, but that's essentially just the array of values that we have. Okay, hopefully still not too scary. But now it's time to bite the bullet. If we're going to get serious about this, we actually have to represent types. Types are what real Java programs are. We don't want to just cobble up an array of bytecode, which kind of works. We actually want to load and run a Java class. Okay? So we want to be able to take a Java class, parse it, get some methods from it, and keep them in a repository, the method cache from the overview slide that I showed you. And then from there, if we've got methods loaded into a repository, well, why not just take a static method and execute it directly? So we take a class file on disk, an ordinary class file, compiled by Javac, we load it, and then execute as our test case one of the static methods that it defines. Okay? Now, obviously, to do that, we need representations. We need a data structure within our implementation which represents a class and a method. To distinguish them, they've got this OT prefix on them, so OT class and OT method. That's just our representation of the metadata that's in that class and in the method, respectively. And we're going to parse the file in order to do that. So here's what a Java class file looks like, and as you can see, it's binary and a bit nasty. So the structure of it, which is the important part, looks more like this. You have the standard and rather embarrassing, I think, these days, magic number for Java class files, Cafe Babe, really? After that, we have kind of the major and minor versions of the class file, and because this is really just a teaching exercise, I completely ignore those. In fact, there are rules for how you should parse a class file based upon its version number. I don't do that, and in fact, most of the checking which happens to determine whether a class file is valid or not, well, I don't do that either. If someone wants to contribute a patch which actually verifies the class file, be my guest. Constant pool, we'll say a lot about this in a sec. Then we'll have things like the access flags, the name of the current class, the name of the superclass, and then interfaces, fields, methods, the things we would expect to be in the class file. Okay? So this is pretty much what we expect, but I always find it hard to remember all of these different sections. So I came up with this nice mnemonic. Has anyone ever seen the movie Gremlins? This is kind of my homage to Gremlins. My very cute animal turns savage in full moon areas. Okay, so of all those areas within the class file, there's one we need to pay particular attention to, which is the constant pool. This is a self-consistent set of what the class refers to, not what is available. So it's not like a Unix symbol table. So for example, here is a very simple class, and here's what its constant pool looks like. It defines a method, it defines a field, and the way to decode these is that these numbers refer to other entries in the class file. So it's a self-consistent set that to parse it, to parse an entry like a method ref, for example, you then have to parse two sub-entries. Okay? This is important, as this is going to cause us problems in a sec. Other things which you can see in here, like the name and type, the name of the class itself, the name of the superclass, which obviously is object. So now, here's what we need to build. We need to build a class file parser. We need runtime representations of these things. And, oh, look, we might also build a runtime representation of an object now, OT_obj. And we'd better have a class repo to keep our classes in so that we can look up classes and look up methods when we need them. So back to the demo. Okay, and now you can see that there's suddenly, wow, there is a lot more code here. This is the big step up, to take from something which is just a simple branching interpreter to something which can actually understand class files requires a lot more work. Okay, so the majority of the work is done in this file here, which is the OT class parser. So this is basically our equivalent, our internal version of class loading. We're going to start off, we're going to set our pointer for parsing, reading the file to 0, pass the header, pass the constant pool, basic type information, fields and methods, and not the attributes. Okay, don't bother with those just yet. Okay, so those sections are in the same order as we saw them in the diagram just a couple of minutes ago. So let's just see how we do. Let's just jump into the parse header. So sure enough, we check the first 4 bytes of the file, and that's basically all the checking we do. From there on, we also parse out the major and minor version number and how many things there are in the constant pool. Now, in the constant pool, each one of these is going to be a CP entry. So we set up an array of those and basically pass out each one that's there. And here are the possible different types of what they are. They're what are called the CP types. So it could be a UTF-8 string, an integer, a float, long, double, class, string, and field method or interface refs. And yeah, I'm using default fall through there, which I know is naughty. And in each of these, what we're going to do is we're going to run a constructor based on how many things we need to pull in. So for example, field method ref and an interface method ref, we actually need 2 other reference types into the name and type. And this is really quite messy. So the CP entry type, which we have, really basically is a sort of a super union of, well, is it a number or is it a string or is it a reference to another method, in which case it needs to have 2 other elements which correspond to entries of the constant pool. Okay? So not a nice piece of object-oriented modeling here. But, you know, the good news is we can parse a class file. We also now need, of course, some runtime support as well. So here are the fields and the class types. And we have things like methods by name, methods by class path, constant pool index, which are our data sources. And I've put some explicit types on these because trying to write var for all this stuff was just getting too complicated. I kept forgetting what the types were. So I actually wanted the explicitness there. Okay. So now what we can do is not just integer arithmetic, not just jumping, but we can actually test the main interpreter. And look, what we're doing, we've got a utility class to pull the bytes back, and we can actually load classes from our own class path, and then add them into our class repo, set up the interpreter main with the repo, and now what we can do is we can pull back a method from the class repo and execute it. So we actually have static classes, which I'm looking up by the name of the method and the signature for it. So this one takes no parameters and returns int. Well, that kind of sounds like the methods we've been running up till now. And they will actually execute. Okay, this is great. We can actually execute methods. What else can we do? So at this point, you suddenly think, wow, providing we just restrict to static methods, we could actually implement invoke static at this point. Because now we can look methods up in the repo. We can load in a class. We can put its methods into the repo. So why wouldn't we be able to implement the same logic as part of a dispatch instruction? So we can now load classes, and we can invoke static methods on them. OK, better speed up. So we can now invoke static methods. We can now create objects. And even once we've created objects, it's not just static methods anymore. Now we can do invoke special as well. So invoke virtual is a little way off yet, but this now brings us to the current state of master. So let's do git checkout. Great. And now you see we have loads and loads and loads of opcodes. There's about 80 opcodes implemented now. Okay. And now we also have versions of exec method which aren't just about the bytes. Now we can just pass in a single OT method object and have it execute. And basically, it will unpack it in the right way, and it will now run. And this includes a bunch of test cases, including some inheritance, including some simple fields and methods, and other bits of code which will actually run properly. So now we can actually build up call stacks, and this will execute as well. So, and this is the class reading. This basically will now run all of the classes that are present. It's going to compile up these OC test methods, which are all here, and it will execute them. Okay. So which other one was I going to show you real quick? So this is the static calls example, just to show you a class with actually some opcodes for calling in. Yeah, that all works. Great. So what's the problem? Well, the answer is, it turns out that not having unsigned integer types is painful for dealing with the byte code, and it's just unpleasant. The scoping rules for switch statements, which we've already met. The representation of the constant pool, we've seen all those problems already. The problem really is there's no pointer types. You end up using longs for everything, and what you end up using the long in the case of an object for is to be an ID into some sort of data structure, a heap or a linked list or something like that. And we don't really want to deal with integer-based lookup for everything. And Java, unfortunately, is too high-level a language. Yes, I could go on and implement more of oscillator the way that we have, but I wanted to do something different. So let's talk about Rust. So we want to replicate the simple functionality of the Java implementation. We want a cleaner class parser, and we want to use the more convenient type system that Rust has. This also means dealing with lower-level memory handling, and hopefully, we'll be able to use Rust's famous memory safety to try to do better. So from 20,000 feet, Rust is a bit strange for a Java programmer. It has a very rigid project structure, and the rules for that are not well documented. Do we have any Rust programmers in the room, by the way? Am I going to get lynched for saying some of this stuff? No, good. OK, so the project structure is distinctly rigid, and they do a really odd thing. The tests cases live in the same directory as the code, which I'm still slightly weirded out by. Like, you have your source code, and in exactly the same directory, you have a file called tests.rs, which is where your test cases live. You also have some other odd things about the project structure. It needs to be grouped in a very specific way, and if you get the groupings wrong and the subunits for Rust code, then the environment is very, very unhappy. The good news is the environment is really super easy to set up. The tooling, you just run one shell script or one brew command, and you have the latest version of Rust. It has a nice set of tooling called Cargo. So the command line tools for Rust are very good, and it has a packaging system called Crates, again, which is pretty good, at least as good as Maven, I would say. The other nice thing about Rust is although you recompile, the compilation cycles are so fast that you really don't mind the fact that you are rerunning the cargo clean and cargo build command all the time. It's a statically typed language, and it has very, very strict typing rules, but it has much type inference. It doesn't do any, even kind of integer conversion types under most circumstances. It has lots of low-level types, including helpful unsigned integer types, which we like. And it's not really an OO language. It doesn't have method overloading, for one thing, and there is trait implementation, but there's not really an inheritance hierarchy in the same way. In the code that follows, I have not written many or indeed any traits. As Brian was talking about earlier on, it has algebraic data types, so it has sum and option types. That turns out to be really, really useful for one of the things that we want to do. It uses option types in a load of places, so including things like if you look up into a dynamically sized array, which Rust calls a vec, well, there might not be anything at that index. So array lookup is something which returns an option rather than the underlying type of the array. The first time you see that, it looks a bit weird. It also has nice tuples with destructuring built in and non-erased generics. And Rust's conception of what the type actually is goes far beyond what we've typically seen in Java. In particular, Rust has this thing called lifetime. You actually have to understand how long any value you bring into existence will live in your program for. And the lifetime is itself a parameter which you can genericize over, which is just completely blew my mind the first time I saw it, and I'm still not entirely sure that I understand all the ramifications for that. Rust is, if I had to describe it, I would call it a pedantically typed language, especially about storage. You know, you cannot declare a variable, you have to declare a variable to be mutable. By default, if you just use the let statement, it will not be mutable. So it's immutable by default. You have to explicitly switch mutability on. Mutability also factors into the type. So if you take a reference to something, which you can do in Rust because we have actual pointers and those types of operations, the mutability factors into the type. Hands up if you're a C++ programmer. Okay, so the mutability is like const, I would say done correctly, but also const on steroids. And here is where where all of this pays off. The payoff, the kicker line for Rust, is that Rust will only compile a program which it can prove is safe. A program which it's not sure about, it will not compile. And it's possible to write semantically correct, safe programs which a human being can recognize as being a safe program which the Rust compiler will reject because it's unable to prove their safety using its algorithm. Okay? So that's a huge thing. That basically that you want to try to get as close as possible to the guarantee that if a Rust program compiles, it will run. Right? So segfaults should be a thing of the past. Okay? It's a high price to pay, but I think for some applications it's definitely worth it. One other thing which is also throws people the first time they encounter Rust code. Again, let me use the C++ terminology here. Rust has move semantics. In fact, Rust defaults to move semantics. Now, you might not encounter this immediately because the simple types, such as ints, have copy semantics. They are what Rust terms a copy type. But as soon as you start to build up types of your own, which Rust calls structs, you will immediately encounter the fact that when you create them in storage, they are moved from variable to variable. So you can't take a variable, a Rust struct, and assign it to one variable, and then assign it to a second variable. You're not allowed to do that because the value is out of the variable is out of scope as soon as the value has been moved. Takes a bit of getting used to. Okay, so let's see what we shall try to support initially. We're going to do the same thing as we did for the first Java demo. So just integer arithmetic, returns, and some stack manipulation. Okay. So in the Rust command line, we just do cargo just make sure everything's working properly. There's a whole load of warnings because it doesn't like my code naming conventions, but they're deliberately supposed to be done to mimic the Java ones. Cargo test. Yep, all of our tests pass. So let's have a look at some Rust code. So like I said, Rust is not an object-oriented language. So it's totally fine with the idea that we have free functions. The keyword to define a function in Rust is fn. The methods, it has the type idea that the types of things where they're needed, and I tend to put in more types than we actually need, go after the parameter. So the buffer here is a reference to a vec, i.e. a dynamically sized, array of U8s. Yeah, so no type erasure here. We can totally say, I want a parameterized type of effectively a primitive type. Okay? There are there's no new keyword in Rust. So constructors are just ordinary functions. And so basically that means that I can write a simple factory method like this to say I want a mutable interp local vars. Notice the naming convention here is exactly the same as it was in the Java code, quite deliberately. And then from there, I can call exec method 2 on, and again, I'm filling in the parameters as I did the last time. And that is going to return me opt_ret. So as you can probably guess from the name, that's an option on the return value. Okay? Rust has match expressions. So our match expression here basically has those exhaustive case class branches which Brian was talking about. The reason why I'm showing this in this much detail is this is very much how Java's going to look once we have match expressions. An option, of course, you will remember, has only two possibilities. Either it has something in it or it doesn't. So it has an exhaustive match set of possibilities of the sum subtype, and in languages which aren't Java, option is implemented by having as a sealed type. There is an abstract base called option, and it has two subtypes, which are the only ones possible, sum and none. Those are an example of Rust's algebraic data types there. So in the case where we have a sum value, we return that value. So overall, what this method does is it executes a buffer of code you pass it, and it returns a JVM value by unwrapping it from the option. So down here, we can see the same thing again. I've built up a vector, and the vec exclamation mark means that this is basically going to construct a vector out of these four opcodes for me. Then I pass them in, and then what I'm going to get back, well, you can see that once again I'm using a match expression. And what I'm doing here is the equivalent of a type test. I'm matching against the JVM value. Now, JVM value actually is the other type of subtypes, which Rust calls an enum, which is really, really, really confusing. It's not an enum as we know it in the Java sense of something which only has a finite number of distinct instances. An enum in Rust is what has different subtypes, each of which has potentially a different carrier. So we can be strongly typed. This works out to be really useful. In the case where we return an int, we match the int value to unwrap the result of this from being a JVM value back to being an int, and then we assert that it's equal to 2. This underscore is, of course, the default case, as it is in many other languages. So if we get back something from the execute method, which isn't a JVM value int, we will just throw an exception here. Okay. And sure enough, we have a few more test cases like that. So let's actually take a look at the interpreter main loop. There are two methods, the exec method and exec method 2, because Rust doesn't support method overloading. You can only have one method of a given name. So that's why the crazy 2 convention here. We implement the opcodes, and once again, that's done using a loop, which is Rust's really only loop. We take each bytecode and notice once again that we get that back by calling get on the dynamically sized array. We match it, and we get back an option. So once again, we have to unwrap the option in order to get the value out. We can then match on the instruction that we've pulled out. And all of these, instead of being enum types and type safe as in Java, all of these are just constants. So you can see that the structure of the interpreter is much, much clearer. And I think to finish with, slightly over, I won't run the class path, but what I will do is I will just switch to master and show you the full extent of what's been implemented. Rebuild, because compiled language, so there's no IDE for all of this. There's VS Code. And now you can see we've got a whole bunch more stuff implemented, including something which will take the OT method type. And sure enough, we have a runtime crate, as they're called, which can hold a bunch of other things. And you can see that the names of these types are all the same as previously. So the class parser is much, much nicer. And this, by the way, is how Rust implements object orientation. You have an explicit self parameter, just as you do in Python. So now we call these methods in order in exactly the same way. The code is just easier to read, I think, and nicer because it doesn't have so many byte manipulations and bits that we have to flip. We also pull back the different types. So each of the types that are present in the constant pool can be represented without that horrible, clumsy subclassing that we had to do in Java. They're just represented as a Rust algebraic data type of the different possible cases, a sum type, if you will. Okay, so that's the class parser. And now let's see some of the main ones. So now we can have a simple invoking class. And in the main loop, this is why I didn't put in too many opcodes at the start, because it makes the switch statement really, really big. So we now have the ability to dispatch onto an individual class object, individual methods that we've looked up. I'll just show how the dispatch works, and then I'm done. So you pass in current class, the index that you want to look up, you pull that back, and then if it's a method ref, you dispatch based on that. And then you call the exec method to actually go into the interpreter loop. Okay, so there's way more there, but I only have 50 minutes, I better stop. So what's still to do? There's a representation of the class repo that we need to talk about. It's currently using Rust mutexes. The OT class loading has to be mutable, but only temporarily. So the current implementation is mostly immutable, but to support things like native methods, we actually need to have a class that we can modify after we've loaded it. It's unclear how to do that yet. I'm playing around with a few things. And there's a big question about how we manage the Java heap correctly. This turns out to be the trickiest part of the implementation, because if you do it using a mutex to basically say, I want unique access to the heap while I create an object or mutate one with a put field, for example, you get deadlocks. So I banged my head against that wall for about 2 weeks and couldn't figure out how to solve it. So I'm going to try 3 more things which are also available in the advanced Rust toolbox. A thing called a cell, which gives you the ability to have something which is mostly immutable, but one part of it which can be separately mutated from the rest of the object without affecting the constness of the rest of the data. There's also a garbage collector. And that's kind of crazy. Rust doesn't have a garbage collector, but someone has actually implemented a GC that you can run on top of Rust itself. And then finally, just as in Java, Rust has its own unsafe mechanism where you get to break all the rules. Given our experiences as Java programmers with unsafe, that's kind of bottom of my list of things to try. I kind of feel like I will have failed if actually I have to implement this using unsafe, because the memory safety was the whole point. So overall, Rust has been a great learning experience so far. I've got a long way to go with it. I would recommend it to Java programmers who want to try out a language which isn't one we're familiar with. It has loads and loads of really nice stuff in it. and it's been a great exercise so far. We're hiring at New Relic, as always, so if you have questions or you want to come talk to me about New Relic, or you want to critique my code and tell me that I'm terrible at writing Rust, then please do that as well. Okay, thanks very much.